what we'll do today first is consider how we can test for the presence of spatial correlation, and specifically in the residuals of a regression model. So the idea is, how can we, in a specification search exercise, move from a standard model, a standard linear regression model, look at the residuals, and from these residuals move on to an appropriate spatial model. That is the main message, main purpose. And so once we're there, then the second aspect is, given that we have decided which of these spatial models it is, how do we estimate the parameters of this model? So I'll start by very quickly, again, getting everybody on the same page in terms of terminology and covering some regression specification issues, and also in the process illustrate some of the specification tests that are built into GeoDa. And then cover some principles of testing specifically for spatial autocorrelation. This parallels in some sense what we talked about on the first day when we talked about descriptive spatial autocorrelation tests. So it has to do with what is spatial randomness in a regression context, and then what are the alternatives. And then we move into two types of tests, two types of test statistics. What I call spatial autocorrelation tests are also referred to as diffuse tests, in that the null is always spatial randomness. The alternative is some form of spatial correlation, but it's not specific what model this is. Whereas maximum likelihood-based tests are also referred to as focus tests, have a specific alternative in mind. And specific in our context will be either a spatial lag model or a spatial error model. So the idea is then to be able to carry out a specification search where you start with a least squares regression, the residuals, to carry out diagnostic tests, and from that you determine which is the proper alternative model, and then we move on to the second phase, which is estimation. Just to get everybody on the same page, the frame of reference, the null hypothesis, if you wish, is the classic linear regression model. In matrix notation, a vector of observations on the dependent variable y, a matrix of observations on the explanatory variables x, a vector of regression coefficients beta, and then the error term u. And it's actually quite a restrictive framework, the classic setting, in that we have to assume a whole bunch of things. A correct specification, namely that it's a linear model, no omitted variables, and more specifically for our context, that the error terms have to have a constant variance, which we refer to as homoskedasticity. So the absence of a constant variance will be referred to as heteroskedasticity. Say that 10 times. And then the second one is the uncorrelatedness. And we'll be particularly interested in deviations from that have a spatial ordering or a spatial structure, which is our spatial autocorrelation. The alternative, as I mentioned, one of them is anything that doesn't fit into that framework. So the ones we will be interested in are heteroskedasticity, the lack of a constant variance, or correlation, either induced by a spatial error alternative or induced by a spatial lag model. Before we get into the technicalities, it's important to know that both of these alternative models will tend to result in residuals of a regression that are spatially correlated. The challenge will then be, how can we tell from the spatial correlation in the residuals which of the two, the lag or the error, is the proper alternative? And as we saw yesterday, there is a major difference between the two in terms of substantive interpretation and also in terms of the consequences of what happens if we ignore it, the lag model being much more serious than the error model. Another problem that we encounter in practice is that there is no guarantee that there is only one deviation from the null, from the classic set of hypotheses. And there could be multiple combinations of these alternatives. So we could have situations we don't really know when we do the estimation what the true model is, what the correct model is. So we could have situations where there is both heteroskedasticity and spatial correlation, and the challenge in applied work is sorting out which is which, and in some cases, as we saw yesterday, there isn't enough information in the data to sort this out, and we have identification problems. So in practice then, the challenge is, given these residuals, how can we tell whether it's a lag model or an error model, or whether it's heteroskedasticity? And one of the problems, as we'll see later on, is that most of these test statistics have power against multiple alternatives. So specifically, if you use a standard test against heteroskedasticity, it has power against spatial autocorrelation. Now think about this for a second. Why would this be the case? Going back to yesterday, we saw that several of these spatial processes, the moment that the number of neighbors was not constant, induced heteroskedasticity. So if you use a test to check for heteroskedasticity, it may pick this up, but it's not true heteroskedasticity. It's the byproduct of the spatial process that is working on the error terms. And similarly, we have the same problem the other direction as well, in that some test diagnostics for spatial correlation, Moran's eye specifically, is a very powerful diagnostic, and it picks up alternatives like heteroskedasticity or non-normality and so on. So the challenge then is, how can we tell which it is? Because you carry out these diagnostics, they reject the null, but they don't tell you what the alternative is. And that is what goes on in the specification search, and we'll talk about this at the end. There are really a whole range of diagnostics, and some of these are more formal than others. And I just wanted to start with some informal diagnostics. The rationale here is that residuals should not show any systematic pattern. Now, there is a fundamental difference between the error term in the model, which we have called U here, which is unobserved and is basically just a mathematical concept. This is not something real that we can see. And the residual, which is the difference between the observed and the predicted value, which we can very much see and measure. The complication is that there is a connection, luckily there is a connection between the residual and the true error, but it is not an exact connection. And residuals have some properties that the true error might not have. For example, least squares residuals by construction are correlated because they extract information from the same data set. Even when the error terms are not correlated, the residuals are somewhat correlated. So then the trick is to distinguish this built-in correlation of the residual from the true correlation that would be the result of a spatial process working for the error terms. And this is why we have specialized test statistics. And as we'll see in a few minutes, the Moran's eye that we apply to residuals is not the exactly same Moran's eye as the one that we talked about the other day, used as a descriptive statistic. So these informal diagnostics are ways to use the residuals to get some insight, to get some suggestion of problems with the true unobserved error terms. So what we're doing here is use plots or graphs or maps of the residuals, and if there is a systematic structural pattern in those residuals that might suggest that there is a similar structural pattern in the error terms. Errors should not show any pattern at all. And the idea is then, if the residuals don't show any pattern at all, then we should be fine. If the residuals show a pattern, the errors may or may not also show a pattern. That's the way to put it into perspective. And these plots are geared at finding very large residuals. These are indications of observations where the model fits very poorly. And this can be due to a number of reasons. It could be due to coding mistakes, or it could be due to structural instability, that the model really doesn't fit the data well for particular locations. And what you're looking for in these informal diagnostics is any kind of systematic pattern in this. For example, if you would look at the residuals and you find that the 5 largest residuals are all in neighboring census tracts, that would raise a flag and say, well, something systematic might be going on here that we're missing in our model specification. This is not a test statistic. This is informal. But it's just like the exploratory data analysis we talked about the other day. It's often very efficient in that it very quickly points to potential problems in your model. Another important thing to do is checking for symmetry. If the residuals are highly asymmetric, that may point to some problems with the model as well. A standard plot is to plot the residuals against the predicted values, and basically what you're looking for is any kind of systematic, like funnel type pattern which might suggest heteroskedasticity. And there are a number of these informal plots.
I think another one is just to plot them on a map.
Yes, that comes next.
Oh, sorry. Oh, that's right. You're still in OLS.
Yeah. So we have different plots, and then we can do a Moran scatter plot, which you practiced in the lab the other day, for the residuals. Now, it's an informal thing. This is not a statistical test. So what you do is you just create the Moran scatter plot, and under the null, the slope should be more or less 0. And if it is not, then there is a suggestion that there might be a problem. But it's not a test. Why not? Because permutation is not valid for the residuals. Now, bootstrapping is another story, and I don't really want to get into this, but the permutation which we've used the other day to build our empirical reference distribution is not valid because the residuals are already correlated by construction. So you really need to, strictly speaking, you should be able to filter that correlation out of them, and then you could permute them. And in the 70s and the early 80s, this was quite a bit of a literature in creating these kind of residuals, which essentially means that instead of n residuals, you would have n minus k residuals, which would then be proper and uncorrelated, but we never really get into this. So it's something to be careful with when you, for example, use GeoDa. You can make a Moran scatter plot for the residuals, but don't run a permutation test because it is invalid. So here's some examples of these plots. This is a plot of the predicted and the residuals against the predicted, and what we want to see is kind of a parallel band, and if anytime we see this kind of funneling, that raises a flag. We have a Moran scatter plot. In this case, it doesn't really tell us that much. It's not 0, but whether this is significant or not, we don't really know. There is a suggestion of spatial correlation. And then obviously we can also map them, and we can look at whether there is any kind of systematic grouping of the high residuals, of the positive residuals, the negative residuals. In other words, is the systematic over-prediction in particular regions of our data, or systematic under-prediction in regions of our data, which suggests that there is something going on that we are missing that has a systematic spatial structure. We have to be careful with this because, as we know, these choropleth maps, they're basically like histograms, so they do simplify the continuous distribution into categories. And we can, in GeoDa, as we'll do in the lab this afternoon, you can, the power really of these informal diagnostic plots is the linking and the brushing, is that you can have a residual plot, a residual map, as well as maps or plots of other variables that might be of interest, and then by linking them, you can start seeing Well, this region where I have systematic overprediction is one where this variable, say income, is systematically lower than in other parts, and income is not in my model, so maybe if I bring income into the model, this systematic patterning will go away. This is the ideal. The ideal of diagnostic checking is not to do tests for the sake of doing tests, but to have the test statistics inform you to move to a better specification of the model. So in the ideal situation, you carry out these diagnostics, you see something that says this variable that I have not included in the model should be in the model, I include it in the model, and then any systematic pattern in the residuals goes away, which means whatever is left is noise. I cannot do any better in terms of my model. That's the ideal. How do we get there is as much an art as a science, because there are, as we'll see later on today, several very serious methodological and even fundamental statistical problems in this process in a classical framework. In a Bayesian framework, it's very different, because the Bayesian framework is essentially an information gaining framework. It's a decision-making framework. So everything builds on information that you already have. In a classic framework, you get in trouble the moment you do more than one test. And then the p-values are related to each other, and sorting that out exactly becomes very complex. And we'll talk a little bit about that later on.
Could you say something about doing Lisa tests on residuals?
Lisa tests are inappropriate in a strict sense on residuals, because the inference for them, at least in their implementation in GeoDa, is based on permutation. And so if you, what you should do, but it's very difficult to do, is filter out the built-in correlation and then carry out the permutation, or use some other inferential mechanism, and then it would be fine. If you would take them as residuals and then do the inference taking into account that these are residuals, then it would be fine. But the way it's implemented is really not appropriate. That doesn't mean you can't do it as a rough guide, and that doesn't mean there isn't some value to be gained from looking at these Lisa maps, that in the sense that they might suggest some patterns, but this is very informal and very non-rigorous, in the sense that these p-values that you are counting on are almost certainly incorrect. So they give you some suggestion maybe of a clustering, but they are not tests for local spatial autocorrelation in the sense that we saw the other day as a descriptive statistic. So these maps look something like this. What you're interested in is, this is a standard deviational map of residuals in a regression model, and what you're looking for are systematic patterning of high and low values. So for example, you could say, well, there's all these browns and reds in the upper left corner. How likely is that to happen randomly? So we might be interested in testing for spatial autocorrelation. As we saw the first day, it's very difficult to assess this by eye. But it's not impossible, in that if it's really extreme, you will see it. It's when you get into the range where the autocorrelation is there but rather small, as we saw the other day. If we have, say, 0.2 or 0.5 in these simulated patterns, it's really hard to tell that apart from the random pattern. But once you get into the 0.7 and the 0.9, it becomes very clear. And this is the sense in which that these informal plots may be useful, in that when the problem is really extreme, you will see it. The formal test statistics are much more useful when the problem is more subtle, because then you will not see it. Then you need a proper p-value to assess the probability that your null hypothesis is still valid, and that's what the tests give you. And what I want to do is just give you a quick review of what is in GeoDa in terms of classic specification tests. So we have these informal plots. We can as we'll see in the lab this afternoon, you can save the residuals, save the predicted values, and then use them in any map or plot that is in the system. So you can plot residuals against predicted values or plot them by observation number, and anything that shows any systematic pattern should raise a flag in the analysis. And we have, of course, residual maps. Then we also have a number of traditional test statistics. To begin with, against normality. Why is normality important? This is actually changing a little bit over time. When you work with small data sets, normality is very important because that is an assumption that gets you the inference. When you work with larger data sets, you actually don't have to assume normality because you get it through the central limit theorems. By going to the limit using the asymptotics, you get the normal distribution whether or not you start with a normal distribution. That's a major qualitative difference. So whereas, say, 10, 20 years ago, testing for normality was very important because a lot of your statistical procedures were based on an assumption of normality in finite samples. And if you remember the other day, when we talked about the finite exact inference for Moran's eye, for example, it required an assumption of a normal distribution. Now, once you go to large sample inference, you don't need that anymore because you get it from your central limit theorems, and you can work with much less restrictive assumptions. For example, just an assumption of symmetry might be enough to get you the asymptotics. But sometimes it's even less than that. It's just the existence of first or second order moments, variance being finite, things like that will get you the limit properties depending on the complexity of the model. So that's a very different frame of mind. So the testing for normality, which used to be very important, let me put it that way, is actually not that important. And the fact that you reject normality does not mean that some of these procedures no longer hold. As we'll see later on today, the original derivations of some of the maximum likelihood-based procedures assume normality. In the more recent literature, these same properties hold even in the absence of normality. So you don't need the full assumption of a Gaussian distribution to get a maximum likelihood estimate that assumes a normal distribution. This is called pseudo-maximum likelihood or quasi-maximum likelihood. And you get the same properties in the limit. The only thing you have to do is be careful in terms of the standard errors. And there may need to be some adjustment of the standard errors. But life is a lot simpler than it used to be because of the asymptotics and the central limit theorems that get you there in many more situations than the very strict assumption of normality that was the textbook case even 10, 15 years ago. GeoDa has a Jark-Barat test, which is basically a Lagrange multiplier test or score test that focuses on two moments, the third and the fourth moment. A normal distribution has to be symmetric. So if you find evidence of asymmetry, that is an indication of the lack of normality. And the normal distribution also has particular shape at the tails, which is measured by the fourth moment, or the kurtosis, as it's called. If the tails are thicker than they should be, which really means that extreme values are more likely than they would be under the normal distribution, then again, that's evidence to reject the normal. So this test is in GeoDa. Then we also have some basic tests against heteroskedasticity. And this is very important in this context because, as I mentioned a few minutes ago, heteroskedasticity is so hard to distinguish from spatial correlation. So it's good to have, from a practical point of view, it's good to have some evidence of possible heteroskedasticity. And as we'll see also tomorrow when we discuss spatial heterogeneity, the heteroskedasticity is a major part of that. And in applied work, especially as our data sets get larger, it is almost impossible to avoid some degree of heteroskedasticity, so you have to deal with it. And we have 3 tests in GeoDa. The Blois-Pagan test is a classic Lagrange multiplier test. The Kunker-Bassett test is basically the same, but with a robustification, if you wish, that does not rely as much on the normality of the distribution. And then the White test, which you probably all know, is a specification robust test, in that it does not assume a specific form for the heteroskedasticity. It's basically a catch-all test against a wide range of different forms. Not all, but a very wide range. So we have these in there, and what you typically see in GeoDa is this kind of a diagnostic, where we start with the multicollinearity condition number, which is actually not a test, but is simply a characteristic of the data. The rule of thumb in the textbooks is if you have 30 or more, you're in trouble. In practice, there is really no hard cutoff. Obviously, the higher this number gets, the more trouble you will have with multicollinearity, but I've seen them in the hundreds. If you do trans-surface regressions, you can get them in the thousands, and things still don't blow up. But it is something to watch out for, because basically what it tells you is that your explanatory variables in the model are not providing you with as much information as you might think they do. In that part of the explanation given by one variable is already contained in another variable, so they're not each contributing independently. Then the Jacques-Berat test, in this particular case, we strongly reject the null. And I'm showing you this slide because this is fairly typical of what you run into in applied spatial regression, is that all of these null hypotheses get rejected. So normality, forget it. Heteroskedasticity, strongly rejected. And then, as we'll see next, spatial autocorrelation, also rejected. So this is a fairly standard practical case. The question then is, how do we proceed? And what we'll see is that there's essentially 2 ways to approach this, depending on your personal taste, as I like to put it. One is to pursue the spatial autocorrelation track first, and then the heteroskedasticity part. The other is to deal with the heterogeneity first, and then the spatial autocorrelation part. And in the end, they should all end up at the same point. And it's really a matter of taste. The problem, the complication is, of course, that the sequencing of these tests affect their p-values. And this is called pre-testing. And we'll talk about this more when we talk about specification search. And in a nutshell, it's the following problem. If you carry out a test, there's always a chance that you're wrong. And your second step is conditional on the first step. So the second step depends on the probability that you're wrong in the first step. So then the p-value of the second step is really also tied to the p-value of the first step. So in the second step, even though you think my p-value is 0.05, it is not, because it is a function of what you decided to do in the first step. And we'll see that more specifically later on. And this is called pre-testing. It's always a problem when you do sequential tests. It's a variant of the problem of multiple comparisons that we talked about the other day in the context of the leases. It's in a classical framework, anytime you do more than one test, the p-values are corrupted in some sense of the next stage. And the contrast with the Bayesian analysis is that in a Bayesian framework, you have prior distributions and posterior distributions, and the posterior distributions build on the data in combination with the prior. So the prior information, which you can think of as the result of the previous test, gets combined with the data to give you the proper distribution for the next step, and you can just keep chaining these things together, and everything hangs nicely together. In a classical framework, this is a big gray area that if you want to approach it formally, it's incredibly complicated. And in practice, most people kind of fudge it and just, the one thing to remember is that your p-values are probably not correct when you do a lot of these test statistics. Okay, time to get a little more formal and focus on specifically tests against spatial autocorrelation. The point of departure is the null hypothesis, and the null hypothesis is obviously the classic regression model with all its assumptions. For our purposes, the most important assumption is that the variance-covariance matrix of the error terms is sigma squared I, meaning sigma squared constant, so homoskedasticity, no heteroskedasticity. The I identity matrix implying 0 off-diagonal elements, so no spatial autocorrelation. The alternatives of interest then are twofold, primarily. One, the spatial lag model, which we saw yesterday, the mixed regressive spatial autoregressive model with the rho WY and the X beta in there. And the other, the spatial error model, where the error variance covariance matrix now is no longer diagonal, but has non-zero off-diagonal elements. It becomes a spatial covariance when that off-diagonal pattern has some spatial ordering, which in our case we can get from a spatial error process, and that's going to be important in formulating the alternatives. And then of course we have higher order processes. We saw several examples of that yesterday, combinations of a spatial lag with remaining spatial error correlation, or combinations of error correlation with heteroskedasticity. And the bottom line is, it's not because you focus on one particular alternative that means that there are no other alternatives out there that might also have caused particular patterns in your residuals. So that's important to keep in mind. The framework that we use, and this is again mostly to get the terminology straight for everybody, is we distinguish between a constrained model and an unconstrained model. And this is often, if you haven't worked in this area, this is often not totally intuitive, because the constrained model is the model without the problem. So the constrained model is a model where you force the parameters you constrain the parameters to a specific value. In this case, 0. So if you think of a spatial lag model, so we have rho WY plus X beta, and you constrain the rho to be 0, what do you have? You have a model without a spatial lag, which is your standard regression model. So you can think of the standard model as a constrained form of the spatial model, with the specific constraint being that the spatial parameter, the spatial coefficient, is set to 0. So in effect it disappears. And that's the framework that we use. So the constraint is something that we will test. We will test the validity of imposing a constraint of 0 on this parameter. If the data support it, we cannot reject a null. If the data don't support it, then we reject a null, that there is a constraint that sets this parameter to 0, in favor of an alternative that says this parameter is in fact not 0. And when it's not 0, then we have a lag model or we have an error model. So the constraint in our notation for the error model will be lambda set to 0. The constraint for the lag model will be rho set to 0. And then the alternative is when these are non-zero. And I've kept it simple here and only considered a single alternative. Obviously, there are all kinds of combinations possible, where one is 0 conditional on the other one being non-zero, or conditional on the other one being 0, or they can both be non-zero, and we'll talk about that later. So that gets us into the practice of specification testing, because as I mentioned a few minutes ago, it's not because you're focusing on a particular alternative that is the only possible one that causes the specification error.
So another alternative might be that there's a different spatial process in one model, or use the wrong weights?
Correctly. Yeah. So the weights don't really matter here in terms of the constrained model, because under the null, the weights are irrelevant. Under the alternative, they matter. And so the alternative is where the power of the test comes into play. So when you think of specification testing, it's all formulated in the context of the null hypothesis. So you get evidence that the null hypothesis may not hold. And so you reject the null hypothesis. Now the next step is really up to you. The next step is not part of the rejection of the null hypothesis. The next step is for you to decide what is it that caused this null not to be valid. And this is where the power of the test comes into play. How well is the test able to point you in the right direction? So if a test has power against a lot of possible alternatives, it's no good. I mean, it's good in the sense that it will tell you you have a problem, but it's not good in the sense that it doesn't tell you what the problem is. And that's the second step, and that's where the weights come into play and the spatial processes come into play. And one of the problems that we'll see later on is that some of these tests really don't tell you whether it's a lag or an error, or whether it's an autoregressive error or moving average error process that is the one that is the proper alternative. What they do, and that's what they're designed to do, is reject the null. So they can tell you this rho or this lambda is not 0, but what is the alternative, that's another story. So as I mentioned earlier, I like to distinguish between two categories of tests. One I call spatial autocorrelation tests, and these are test statistics that have diffuse alternatives. So these tend to be very good, what we call misspecification tests, in that they tell you something's wrong. They tend not to be that great in terms of guiding you to the next step, because the alternative is non-spatial randomness. But what exactly, what form it takes, it doesn't necessarily tell you. The other tests are more restrictive and more focused, as we call them, in that they're put in a specific context of a specific alternative model. So this is the case where you set as the null, say, rho equals 0, and the alternative is a spatial lag model with a non-zero rho and a specific weights matrix. So there's a very specific alternative. And then, of course, as long as that specific alternative is really the one causing the misspecification, you're doing great. You get in trouble when you think it is a spatial lag model, but in fact it is a spatial error model that is causing the misspecification. And what you have then is the problem of distinguishing which test points into which direction, and we'll talk about that.
You have a robust test to kind of help you guide between the lag and error model, at least pointing out the third component involved in this thing, which is the weight matrix. So if you keep it constant, then you can use these two tests as guide. But I think what she's suggesting is it may be sensitive to the weight matrix that you use. So if you tried a different weight matrix, you get the different alternative models with different tests. So how do you decide what's important at work here? Hopefully theory guides it, but doesn't always. In other words, what do you do about the weight matrix? Just try a different weight matrix, run through it again?
The
best result?
There are, the question is, what do you do about the weights matrix? And there are two issues here. And one is, strictly speaking, the test is about rejecting the null. So as we mentioned the other day, what you want is a weights matrix that is good at helping you reject a null. This may or may not be the weights matrix that you eventually want in your model, because the test as such doesn't really tell you what the alternative model is. That's the limitation of hypothesis testing. You know, the hypothesis test does not accept the alternative. It rejects the null. Okay. So the weights matrix that you use in specification testing, the way I look at it, should be useful in rejecting the null. A second step, a second stage, and a much more difficult stage, is picking the alternative. And so say you reject a null in favor of a spatial lag model. Then it's up to you to specify that spatial lag model, and you can take a number of different weights matrices. Now the weights matrix that you used in your test will typically have power against lag models with different weights matrices. So because it helps you reject the null. If you have, say, model A with a weights matrix, say, based on simple contiguity, and model B with a weights matrix based on economic distance. And let's say model B is the true model, but you construct a specification test using contiguity weights. Because model B is the true model, your least squares model will be misspecified. And there will be a spatial patterning in the residuals of the least squares regression. The test using the wrong weights matrix will pick that up. Will it pick it up as much as if it used the correct weights matrix? No, but it will still pick it up. And so it will tend to reject a null, which tells you I am not okay with my simple least squares model, but it doesn't really tell you, that's where it stops. It doesn't really tell you that it's model A or model B that is the correct alternative. And so then, in practice, you're basically stuck. And so then what you can do is move to a different frame of mind, which is a model validation frame of mind based on fit. And what you can then do is run a model A and run model B and see how they compare in terms of how they fit the data. And that then is a practical criterion. It's not based on hypothesis tests. There's no p-values here. It's like comparing R-squares. That's not a test, but that's a measure, a metric that you can use to compare how well your models do.
There must be some sort of way to think about this theoretically, though, in terms of how we expect our understanding of the system that's out there, how things are acting spatially, right? Like the shopping center attracting customers or whatever's going on, contaminated site affecting values, or some sort of understanding of the system that gives us a sense of how this would operate, right? That would help us specify the model.
Well, yeah, ideally you have a strong theoretical framework that tells you, I mean, remember our discussion the first day was about modeling spatial interaction. So if you have strong insights from theory or previous empirical work about the form and the nature of that spatial interaction, that should drive the model that you use. In practice, there are often a small number, sometimes a large number, of competing formulations. And it's not clear a priori which of these is more valid. And then it's really not a hypothesis test situation, but it becomes a model comparison situation. And there are different criteria. And in a strict sense, it depends on your objective function. What is it that you're trying to do? And in a statistical decision-making framework, the objective function should come first. So what is it you're trying to do with the model? And say that is get the model that fits the data the best, or get the model that gives me the least chance that I make the wrong decision, which is quite a different framework. And then each of these objective functions then determine how you would compare the models. And that's really the only way to think about it. And it doesn't fit well in strict hypothesis testing. It moves beyond that. It's part of statistical decision making. And here again, a Bayesian framework is ideally suited for that type of reasoning, because everything is building up information in function of a particular decision. In the classical framework, there's lots of ad hoc decisions that are made in this process.
What if we assumed that that there was a lag model and actually there was heterogeneity in the lag, in that urban or rural spillovers were different, or red state, blue state spillovers were different. After we ran the lag model, would there be some indication that there was still a problem?
Yeah. So okay, the problem is if you run a lag model, but in fact there is heterogeneity, after you run the lag model, would there be evidence of this? And this is part of the specification search, in that the general principles that we'll talk about in a non-technical fashion, for example, the Lagrange multiplier principle, can be applied at any stage of the modeling. So after you run a spatial lag model, you can test for heteroskedasticity, or anything else for that matter, remaining spatial correlation. The problem with these tests is that they become sequential, so you have to worry about the exact p-value. Now, in practice, this is going to be a problem when, as I like to call it, when you're on the bubble. When you're at 0.04, 0.03. But if you have, as you will see in a lot of cases, overwhelming evidence, especially in larger data sets, it's not an issue. I mean, sure, your correct p-value might not be 0.000001, but what does it matter? It's close enough, and it's going to be a strong rejection of the null, right? It's when you are at this boundary level in your decision process that you should be aware that the p-values that the software gives you in the sequential testing setup is not going to be right. And that is a problem, as it's called, of pre-testing. So in terms of the test for spatial autocorrelation, we have what I would like to call two frames of mind. One is a misspecification frame of mind, which is great when your model is good, in the following sense. You carry out these misspecification tests, they do not reject to null. You're fine. If they do reject a null, they are less helpful because they do not provide a suggestion as to what the alternative might be, so you're back to square one. You have to go back and rethink what should my model be. The other tests are much more specific, which is both their strength and their weakness. It's their strength in that they do tend to suggest what the alternative is. It's also their weakness, because if this structure is not the correct structure, then you have additional misspecification. For example, if you are testing very specifically for error, but in fact the true alternative is lag, you will make a mistake. And that's where the robust tests come in that try to correct for this. But this is the trade-off. So the more you assume, the more structure you put in, the more likely you're making a mistake in terms of the structure that you impose on the data. The less structure you impose, the more likely you are to catch specification problems, but the less likely you are to actually know which one it is that causes the problem.
When it's clear, when the robust tests clearly guide you to a lag model or to not use an error model or vice versa, that seems a reasonable guide. When they're not too clear as to which way to go, what course of action is suggested?
The question is, when it's not clear whether the alternative is a lag or an error, and we'll actually get to this later today, but just running ahead on it, to remember there's lots of things that can go wrong in a model. And my take on when there's not a clear distinction between lag and error, and this happens, say, in very large data sets, is that there's a lot of other misspecification going on. And one of the first things I always go back to is the weights matrix. Another thing might be just the fundamental specification of your model. Maybe you need a log linear model or something else. When you have strong evidence of high spatial autocorrelation, both lag and error, there's something not right. That is the message that you get from that. And then sure, you could say, well, this one is a little bit more significant than the other one, so I'll go lag and put on my blinders. But then if you do that and you do an additional test for remaining error correlation, it will be there. Okay. So let's see. Let me quickly go through this and then we'll take a break. So most of this I've already covered. So the two tests, the diffuse and the focus test, the spatial autocorrelation test, they don't have a specific spatial process as a alternative, and they have power against both. They are based on detecting deviations from no spatial correlation, so they're good at that, but they don't tell you particularly what the alternative might be. So Moran's I is as an example. Moments-based test, moments being cross products of residuals, things like that. In the absence of autocorrelation, those cross products of residuals should not show any systematic pattern. That's the rationale behind these tests. And then the other tests are based on a full specification of the likelihood, which means you assume a distribution, full specification of the model, and then, of course, with that structure, you are able to derive some very powerful test statistics. And the three that we will focus on are the Lagrange multiplier test, which is also called the score test, the Wald test, or also called the asymptotic t-test, and then the likelihood ratio test. And then there's some other variants, like a double-length artificial regression, which you should be aware of and you might try, but they are based on the computation of eigenvalues. And remember my comment the other day, anytime you see a method that requires eigenvalues, you know that it's going to be limited computationally as soon as you reach several thousands of observations. Now, if you don't, then it's perfectly all right. But if you do, then this is not going to work. Whereas these other methods, they don't require eigenvalues. They just require cross products of residuals weighted by spatial weights and various traces of weights matrices. These are things that can be computed even for millions of observations. So they can be implemented.